Good afternoon, everyone. Thank you for joining. My name is Sayed Behrat Emadi. I am a researcher at University of Salerno. My presentation today will focus on the enhancing point cloud optimization with deep learning models. The use of point cloud technology for 3D recording has seen significant advancement and has become a cornerstone in the surveying and structural monitoring. With the integration of computer vision techniques, point cloud processing has become faster and more efficient, addressing many limitations of traditional photogrammetry. In the cultural heritage domain, where the purpose is to protect, monitor, or document archaeological sites and architectural restoration, accuracy is of utmost importance. This presentation aims to evaluate the optimized various structural from motion parameters to enhance the accuracy of 3D reconstruction. In order to evaluate the role of different parameters, firstly, the work individually analyzes several photogrammetric accuracy parameters in a case study to verify that a single parameter is not sufficient to filter noise from a photogrammetric point cloud. The first parameter calculated is the reprojection error, which is a geometric error corresponding to the image distance between a projected and a measured point. In this work, the base to height ratio was analyzed by estimating the angle between two lines of view that generates the 3D points, called the angle of intersection. Another estimated parameter is the number of images, which is the number of images of the scene that have contributed to the reconstruction of the points in object space. The last value taken into the account in this analysis is the projection accuracy, which allows us to recognize less reliable type points. These parameters depend directly on the image acquisition phase, so that these values can vary considerably from project to project. In order to optimize and enhance the accuracy of the 3D reconstruction models, we will propose an outlier detection method that does not consider a single parameter related to accuracy, but simultaneously all calculated parameters. First, to reduce the dimension of the model from several different parameters to two synthetic parameters, the new model uses an autoencoder network. An autoencoder is a type of neural network used for dimensional reduction and feature extraction. It consists of two parts, an encoder that compresses the input data into the smaller representation dimension called latent space, and a decoder that reconstructs the original input from this compressed form. The goal is to learn an efficient representation of the data. At the latent space of the proposed model, where the feature dimension are reduced to two clustering machine learning algorithms were applied. First clustering algorithm is K-means, which is a clustering algorithm that partitions data based on similarity. It works by assigning each data point to the nearest cluster centroid and then updating the centroid until convergence. The second clustering algorithm is Gaussian mixture model. It is a probabilistic model that represents the data as a mixture of several Gaussian distributions. Unlike K-mean, which does hard clustering, GMM allows for soft clustering as well. Each cluster generated by the clustering algorithm has a different level of noise associated with the available point data within its 3D definition. The cluster data was then compared against the analyzed accuracy parameters to evaluate the accuracy level of each cluster. The statistical and experimental analysis will identify the optimal set of hyperparameter and cluster for each specific case study. For description, the algorithm, Python programming language, and scikit-learn library were used. The case study considered developing this work is a Temple of Neptune, which is a Greek temple in Paestum, Campania, Italy. It was built in 5th century BC. The temple has 6 front columns and 14 side columns. It is one of the 3 best preserved temples in the Greek world, surveyed with aerial photogrammetry by UAV in 2017. The complex spatial articulation of the geometries makes it a suitable stage for the type of qualitative analysis carried out. The UAV used is a hexacopter assembled with a 3-axis gimbal and the installation of Sony Alpha 6500 camera, and a total of 98 photogrammetric images were acquired. A GNSS network consists of 11 ground control points were included for the estimation of the internal orientation parameters in AGIsoft MetaShape using a self-calibrated bundle adjustment. For the purpose of the analysis, a standard section was selected, a 2.5 meter wide, visible in the figure in red. In the first step, we considered the parameters individually to see how the filtering procedures influence the accuracy value. The first parameter considered is the error projection. The best fitting distribution was used to remove value outside the chosen experimental threshold. These thresholds were set at the 90, 95, and 99 percentiles, allowing the removal of outlier or extreme values beyond this limit. A better result for noise reduction is obtained by filtering the point cloud according to the average intersection angle calculated for each type point. Pushing the filter too far compromising the amount of data necessary for representation. In fact, setting an average angle above 18 degrees removes a large number of points associated with the columns, making the object of the survey no longer distinguishable. An appropriate reduction in noise on type points is already noticeable for angles greater than 10 degrees, helping to improve clarity without overlay compromising the point data. Another parameter analyzed individually is the number of images. It was observed that when using more than 10 cameras for the 3D point reconstruction, the number of points in the section is drastically reduced. This not only eliminates noise, but also removes part of the column, significantly reducing the quantity of data and affecting the quality of the reconstruction. Finally, the last parameter analyzed individually is the projection accuracy. The observed trend for this parameter is similar to the number of images. As the filtering threshold value increases, noise decreases. However, pushing this value beyond a certain limit starts eliminating portion of the columns, compromising data quality. The optimal threshold for noise reduction is a projection accuracy of 10. Increasing it beyond this value continues to reduce noises, but at the cost of losing valuable data and compromising data integrity. Feature analysis shows that the use of a single parameter in the reduction of noise in a point cloud is not the best approach. The parameter that best eliminates outlier without affecting the cloud is the angle of intersection. The problem with this parameter is that as the angle value increases, more outliers are removed. But after the threshold value, points belonging to the cloud are simultaneously eliminated, so that the density of the cloud does not allow a good description of the object. To perform the new model, the data was first reduced to 2 dimensions using an autoencoder model. Then in the latent space of the autoencoder model, GMN and K-mean algorithms were applied. To analysis of GMN and K-mean shows that the average value of the parameters are not very significantly different from each other. Comparison of cluster information with the individual analysis parameters prove that accuracy of the new method and shows that both clustering algorithms have similarity and consistency in their result. However, GMM shows better distribution of point data in the clusters. The number of type 1 found in cluster improved the point cloud density while preserving its quality, allowing for a better description of the object. The future direction of our project, we propose to implementation of Siamese neural network to enhance damage detection in cultural heritage sites. This innovative approach will allow for the comparison of point cloud dataset captured at different times from the same location. By analyzing the change between these temporally distinct datasets, we aim to identify and assess a structural alternation, enabling the detection of new damage and the monitoring of ongoing deterioration. It is important to highlight that given the absence of information of a structural failure condition, the ability to create an accurate 3D model using the available data is fundamental to our approach. and therefore proposed method in this presentation is crucial for reconstructing precise digital documentation, which can be used to compare with the current condition of cultural heritage site in order to identify any new damage. Thanks for your attention.